Topic: Electric field due to a uniform linear charge. Objective: to derive the electric field due to uniform linear charge. Consider a uniformly charged rod of length L, whose charge per unit is lambda. We will calculate the electric field at P at a perpendicular distance of A from the linear charge such that the end A and B of the rod subtend angles alpha and beta respectively at P. Consider x-axis perpendicular to the linear charge and y-axis along its length. The electric field at P is the resultant of the fields due to the different sections of the linear charge varying from A to B. Consider one such differential element of length dy at a distance y from the origin. Charge contained in this element dq equals to lambda dy. Distance r of the element from P is equal to root over y square plus a square, and the angle between A and R is theta. The magnitude of the electric field dE at P due to this small elemental charge is equal to k dq by r square, which equals to k lambda dy by r square. From this triangle, cos theta equals a by r, so r equals a secant theta and tan theta equals y by a. On differentiating this expression, we get dy equals a secant square theta d theta. Upon substituting dy and r, we get dE equals to k lambda a secant square theta d theta by a square secant square theta, which equals to k lambda d theta by a. dE makes an angle theta with x-axis, so it can be split into dE cos theta along x-axis and dE sin theta along y-axis. That is, dE cos theta I cap plus dE sin theta j cap. Net electric field at P due to the uniform linear charge is given by integral dE from minus beta to alpha. So, E bar equals k lambda by a integral cos theta d theta from minus beta to alpha I cap plus integral sin theta d theta from minus beta to alpha j cap. Upon integrating and substituting the limits, we get E bar equal to k lambda by a sin alpha plus sin beta I cap plus cos beta minus cos alpha j cap. This is the general expression for electric field due to a uniform linear charge. Depending upon the position of P and length of the linear charge, three distinct cases arise. Let us deal with these cases. Case 1. Electric field on the perpendicular bisector of a finite linear charge. In this case, alpha is equal to beta. So, E bar becomes (2k lambda sin alpha by a I cap). Case 2. Electric field due to infinitely long linear charge. In this case, alpha and beta are equal to pi by 2. So, E bar becomes 2k lambda sin alpha by a I cap. Case 3. Electric field due to a semi-infinite linear charge. In this case, alpha equals to 0 and beta equals to pi by 2. So, E bar becomes k lambda by a I cap minus j cap.